Hi, Basic Calc. These are your day 109 notes. Today we're going to look at an example from the end of the notes on day 108. And at the end of the day 108 notes, we saw that the absolute convergence theorem for this particular series diverges. So in that case, we don't have a conclusion yet. We have to then transition over to the alternating series test to determine whether or not this converges or diverges. And in this case, the alternating series test, there's really those two conditions that we have to prove true. Is this a decreasing series? And then step two is the last term going to 0 as n goes to infinity. So if we can show these two things, then this will converge conditionally by the alternating series test. So one of them is easier to show than the other. It happens to be, we can find that limit pretty easily. But let's talk about the decreasing piece of this. If we think about comparing this series right here to the function f of x equals 3x plus 2 over 4x squared minus 3, we can show that it's decreasing by finding the first derivative, can't we? So that's how we tell where the original function's increasing, decreasing, and we want to see, is this decreasing for x values that are greater than or equal to 1, because that's the conditions that we're looking at within the series. So when we go to find f prime of x in this example, it's just going to be a quick quotient rule there, right? So we need low d high. So d high is 3 times low, which is 4x squared minus 3, minus high d low. D low is 8x times 3x plus 2 over low squared. Okay. So to determine whether this is positive or negative, and we want it to be negative, right? If we were looking for decreasing here. If I distribute the 3 across the top, that's going to be a 12x squared. This is going to be a minus 24x squared. So in total, negative 12x squared. You're going to get a negative 16x over here. And then from the first binomial, 3 times negative 3 would be a minus 9. And then this is all over 4x squared minus 3 squared. So looking at this fraction right here, we definitely know that the bottom's positive no matter what, right? Squaring this, no matter what x is going to make the bottom positive. But for x values greater than or equal to 1, think about what the result on the top is. If x is some value bigger than 1 or equal to 1, you're going to get a negative times a negative, or a negative minus something else, minus 9. The top is definitely negative. And negative over positive altogether, of course, will give you a negative there. So this is going to be the way that we prove the condition for that first part of the alternating series test, is that if f prime of x is less than 0 for all values of x that are greater than or equal to 1, then we know that f of x is decreasing over that interval. Okay, so therefore we've now shown that, yes, this is a decreasing series of terms. And then quickly, the other part of the alternating series test is showing that the limit as n goes to infinity for your sequence 3n plus 2 over 4n squared minus 3. And that very clearly equals 0 because it's bottom heavy. So that part was definitely easier to work our way around. But since it holds true for both conditions in the alternating series test, we know that the original series from n equals 1 to infinity of negative 1 to the n times 3n plus 2 over 4n squared minus 3. We know that it converges conditionally by the alternating series test. Okay. So just to kind of bring in a little bit more of wrapping up what we did in day 108 here, these are the two conditions we want to prove if we're going to be using the alternating series test, that it's decreasing and that the last term goes to 0. Okay, so let's talk about some error within alternating series. So we're going to define something called the alternating series estimation theorem. And the way we're going to do that is I'm going to bring you back to that visual when we looked at the alternating series test of those partial sums. So we know that whatever the first term of the series is going to bring you to some value S1, and that since the terms are decreasing and the next term is negative, we have that the next sum, S2, might be located right here, and then S3 might be right there. and then S4 might be there, and then we'll do one more. Maybe S5 is here. So they're going to kind of like ping pong back and forth and eventually converge upon some limit L. It's eventually where we're headed here. Okay. So if I look at a very specific example, for example, the distance here from the limit to S4 is going to be smaller than the distance between S4 and S5. So I'm going to write down that the absolute value of L minus S4 is less than this distance right here from S5 to S4, right? If we're converging upon that limit, I hope that this statement makes sense to you, okay? And we know that S5 minus S4 is just the fifth term, A sub 5, right? If you take this, the partial sums of 5 terms minus the partial sums of 4 terms, you're just going to be left with whatever the fifth term is. So using this as kind of a baseline here, we can say that in general, the limit minus S sub n is going to be less than A sub n plus 1. Okay, so the error in general is less than or equal to the first neglected term. And we'll see how this applies in a specific example, but if you want to find, let's say, the partial sums out to S sub 4, that the error has to be less than or equal to whatever S sub 5 is. Okay, whatever that fifth term is. Sorry, not S sub 5, but A5 in this case. Okay, let's see how we can apply that to the example that's at the next page. So we have approximate the sum from n equals 1 to infinity of -1 to the n plus 1 over times 1 over n factorial by its first 6 terms, and then what is the max error. So first and foremost, we know that this converges because we know that this is decreasing and the limit as n goes to infinity is 0. So we know this converges by the alternating series test, just really quickly based on those two conclusions. So if we're going to estimate what the sum is based on the first 6 terms, well, when n equals 1, you're going to get 1 over 1 factorial. And then when n equals 2, now we know that this exponent is going to make that -1. So that's going to be -1 over 2 factorial, then plus 1 over 3 factorial. So when we get out to the 6th term here, plus 1 over 5, minus 1 over 6. Okay. This is the estimation that we're going to use for S sub 6. Now, if I go one more term out, what the alternating series estimation theorem says is that the error has to be less than or equal to this term right here. Okay, there's the 7th term in the sequence, that the error is less than or equal to that. So we know that because of the conditions for the alternating series test, that this series does converge. Converges conditionally by the alternating series test. And if we were to, on our calculators, add all of this up right here, we would get that the sum of those 6 terms is 0.63194. Something like that. Okay. So like I was saying, that 7th term, we know that the actual limit that we're approaching has to be less than or equal to this amount. So an error. So A7 is 1 over 7 factorial, which 7 factorial is 5,840, which is a really tiny amount of error. It's 0.0002. Okay, that is the max error. So if we're going to try and find a bounds of within what we know the limit is actually approaching here, according to what we wrote, that the limit L minus, in this case, S sub 6 has to be less than or equal to that 7th term. And therefore, if you wanted to say, let's take this S sub 6 value that we've calculated and then add or subtract the error, we know that the actual limit that this series is converging upon has to be somewhere from, well, this minus 0.0002 is 0.63174. And then the upper limit, if I add on the max error, would be 0.63214. Okay, so we know that the actual limit that this series is converging upon is on this really tiny window. Okay, so a really tight interval surrounding what S sub 6 is. We know that that's what we're approaching. So that's kind of the last piece that we're adding on here to the alternating series test, is that we can estimate the amount of error within a specific sum, if we wanted to find the sum of the first 6 terms, by looking at the next term after that and then adding it and subtracting it from the 6th term and saying the limit has to be somewhere within that range right there. So what we'll do is we'll go over this next time in class, but see if you can try this example. So determine, does this converge or diverge? But this is something that you should be familiar with. Look back at the day 108 notes if you don't remember. Determine what S sub 4 is. We could do that pretty easily. See if you can determine the max error. And then the interval that would capture S, which is the true sum of the infinite series. S is what I called L up above for the limit, but S is the sum of the series. So if you want to write it in terms of S, we're going to do that for part D there. Okay. All right. We'll leave that for class next time. And actually, that pretty much is the end of our lesson, because the next 3 questions are all sample AP questions. And this is something that we'll work on collaboratively in class next time I see you. So there's a question about populations of wolves. So we'll see that next time we're together. Then there's a question about a differential equation that I'm guessing is going to be separable based on part C here. And then the last question that we'll look at is determining within an improper integral some volumes, areas, and so forth. So things that we've seen within the past, let's say, a couple of weeks in our course here, but just kind of a good stopping place to see if we can do some practice AP style questions with the content we've been learning. So that's it for day 109. We will do these AP questions next time we're together. Have a great rest of your day.